Hello, AP Calculus. It's your day off, but I'm here at work. And we are going to look at the homework guide for the next section, 7.2.3. I've already gone through and circled and X'd out a bunch of problems, and I'm probably going to end up editing a good amount down from this one too. But the first few we totally can do. So let's at least jump right into 777, where we're going to take the derivative of a bunch of tangent and cotangent functions. Now let's actually do B and C first, because we can do those right now. B and C are the ones that you should kind of just memorize. The derivative of tangent is the secant squared of 2x. And then, of course, you're going to have to multiply by 2 because of the chain rule. The derivative of 2x is just 2. Cotangent is going to be very much the same thing. The derivative of cotangent is the negative cosecant squared of 2x times 2. And those are just derivatives that you should memorize. Tangent especially. You know, if you're down to the wire and you're kind of deciding what you should plug into your brain, cotangent, not super important, but tangent definitely will show up several times on your AP test, so there it is. Those two are pretty easy. You can clean them up by putting the 2 in front if you want to. You know, I'll do that because I'm making a video for you. But this first one, you know, again, you could memorize a formula for it. There's certainly nothing wrong with that, but I want to show you how to do that problem without memorizing the formula, so I'm going to draw it over here. We are looking at some angle. This is question A, where y is equal to the inverse tangent of 2x. Of course, we should remember that tangent is the ratio of the opposite side to the adjacent side. So we've got an angle here, which we're calling y, and the y is equal to the ratio of the opposite to the adjacent side when the opposite is 2x and the adjacent side is 1, because the tangent is the opposite over the adjacent. So 2x over 1 gives you the 2x that's in there. Now, of course, the Pythagorean theorem would say that the remaining side is going to be 2x squared plus 1 squared equals c squared. And so c is going to be the square root of 4x squared plus 1, which I'm going to go ahead and write down right there, 4x squared plus 1. That's the remaining side. Now, if we're going to apply a little bit of derivatives to this, let's think about this like an implicit derivative. We know that let's take a little bit of trig first. Let's take the tangent of both sides. The tangent of y is equal to 2x. That's kind of the whole, the same statement right there. If we take the tangent of both sides, it'll cancel out. Now we take the derivative. We know that the secant squared of y times dy dx will equal 2. Because we're taking the derivative with respect to x, the x will just go away, but the dy dx has to pop out because of the chain rule. And so what's left here is that dy dx, what we're looking for, the derivative, is 2 divided by the secant squared of y. And the nice thing about this expression is that we can easily tell what it is. Secant is 1 over the cosine. It might be good just to write this down to remember. Secant is 1 over the cosine, or the reciprocal of the cosine. What's up? I'm recording a video. What's up? Oh, hey-oh. All right. Hey-oh.
How do we do that?
I got a little drawer full of them right here, and I'm going to take them to David Tucker tomorrow.
Okay.
All the sauces in one dude.
All right.
Hey, all right. Thank you.
That's what we got so far.
Awesome.
I haven't got the McDonald's. Did they send something to you or?
Not yet, no.
All right. So we gotta.
And I still got that lead with the dentist, too, so.
What?
I had a lead with the dentist still, too, so.
Okay.
First Street Dental, so they gave us something, so.
All right. Yep.
Okay.
Sounds good.
Great, thank you. All right, back to it. Secant is 1 over cosine, and since cosine is the ratio of the adjacent to the hypotenuse, the secant is the hypotenuse over the adjacent, which in this problem is the square root of 4x squared plus 1 over 1, and that's nice. And the best part about that is since we're going to square that anyway over there in that fraction, this is going to end up just being 2 over 4x squared plus 1. Because the square root will go away, and that's your answer. 2 over 4x squared plus 1. It's pretty cool that it works out that way. Shakes out really nice. I like this process because it forgoes you memorizing the inverse trig functions, and that's nice because you don't have to memorize anything. You certainly can memorize them, and nobody would be mad at you for that, but I think this is easier. As far as 778 go, the only one that I'm really interested in right away is A. The other ones, I don't like B at all, and I'll talk about it in a minute. And then C I only kind of like. So I'm only going to require you to do A. So let's talk about that one in this video. The antiderivative, what I think you should do here is, first of all, take that 2 or negative 2 and put it out in front of the integral. That's going to make this much easier for you. Negative 2 times is just a constant, so you can pull it off in front. And the integral of 1 over x, the antiderivative there, is just the natural log of x. Since the derivative of natural log is 1 over x, the antiderivative of 1 over x is the natural log. So this is negative 2 natural log. Technically, you'll see an absolute value around this sometimes, but it doesn't really matter here. I don't like question B because, just as I was just talking about, it requires you to memorize that the opposite of that is the antiderivative of that is the sine inverse of x. And actually, it's 2 sine inverse of x. I mean, the second part is not too bad. It's just 4x squared over 2. Or, if we're thinking about it, 2x squared plus c. I don't like this problem. You're not required to do it, so... for question C, I like even less because it requires the antiderivative of a root, some other constant root to the x power, and I don't like that one bit, but it would be pi to the x over the natural log of pi, evaluated from pi to 0. And I don't want to do this, and you don't either, so let's not worry about it. 779 is a related rates problem, so let's read carefully and map out what we currently know, what we want to know, and think about how we're going to connect these ideas together with some sort of equation, like every other related rates problem. Grain pouring from a conveyor belt falls into the pile in the shape of a cone. The grain is falling at a rate of 8 meters cubed per minute and forms a pile such that the radius is always half the height. So let's translate these two. There's 2 sentences that are in there that I want to translate into mathematical speak right now. The grain is falling at a rate of 8 meters per cubed is going to translate to dv dt, because that is the rate of change of the volume of the cone, how much grain is being added to the cone, and that's 8 cubic meters per minute since it's a rate. And the radius is always half the height. R is equal to 1/2 h, or h over 2. So we want, these are things that we know, we want to know how fast the height of the pile is changing. We want dh dt, specifically when the radius equals 6. And it might be a good idea to make a note right now that the height will be 3. Since we know right away that the radius is always half the height, the height will be 12. Since we kind of were told at the top of the problem that the radius is always half the height, if the radius is 6, the height is 12, because there's that 1 to 2 relationship. It's going to be really helpful to draw a picture of this. Actually, they kind of already drew a picture, so I'm going to use their picture. I'm going to add kind of a base to this cone. The height is kind of this imaginary distance from the tip top of the cone to the center of the circular base. The radius is that distance right there. And unlike most of these cone problems where it's like a paper cup or something with a water cone or a grain cone inside, this is the cone. It's increasing kind of from the top up instead of being emptied out of the bottom. So we don't really need to do a lot of fancy similar triangle stuff. I do know that the volume of the cone is equal to 1/3 pi r squared h. Oh, geez, I wrote pi again. Volume of the cone is 1/3 pi r squared h. Now we do not want to plug in our numbers yet because this is a general formula that works for any volume of any cone, and we don't want to lock in any values yet because none of these values are constant in this problem. So let's take the derivative first, and then we'll plug the numbers in. Now, I don't know about you. I do not want to do a derivative that involves r and h because it's going to require the product rule, and that sucks. Let's not do that. Let's substitute in this relationship right now. Since we want dh dt, let's replace r with 1/2 h, because then the whole problem will be in terms of h, and that'll be a lot easier for us. The volume is going to be 1/3 pi times 1/2, or I'm gonna write it as h over 2 squared times h, like this. Cleaning that up a little bit, we'll have pi on top, we'll have h to the 3rd on top. On the bottom, we're going to have 3 times 4, because 2 squared will give us the 4, and that will give us 12, like that. Now we want to take the derivative. dv dt. When we bring the 3 down to multiply it, 3 and 12 will kind of balance out a little bit, make a 1/4. So we'll have pi times h squared over 4 times dH dt. And now we can go ahead and plug in our information. I'm glad that we did this little math problem right there because R is not a part of the problem. So we're going to plug in 12 for H. We're going to plug in, whoops, I need a pencil there. We're going to plug in 12 for H. We're going to plug in 8 for dH dt, and we're going to solve this problem. We're going to call it good. So we're going to have pi times 12 squared, or pi times 144 over 4 times 8. I'm trying to not use a calculator for this problem. I know that 8 divided by 4 is 2. I know that 2 times 144 is 288. So I believe this is going to shake all the way out to be 288 pi. And that's the answer that I'm going to circle. Of course, I'm going to, this is dH dt. Oh, are we Oh, shoot. See, I made a big old math boo-boo. Sorry, guys. Back it up, back it up, back it up. Ford's an idiot. 8 is dV dt. Whoopsie. I wonder how frustrating it is to watch these videos sometimes when you're you guys at home, because you're like, Ford, what are you doing? 8 is going to equal 144 pi over 4. I'm sure that's something. Times dH dt. Ah, rats. I was hoping this would be something nice. Oh, well. If I multiply and divide all that stuff over, I'm basically gonna multiply both sides by 4 over 144 pi. Just kind of mapping out my algebra strategy here to get it to all work out. These will cancel out, and 8 times 4 is 32. So my answer here for dH dt is going to be 32 over 144 pi, and I'm sure that's something nice. I was really hoping to not have to use a calculator for this, but I just want to check really quick. 32 divided by 144 is, apparently, according to my calculator, is 2/9. So 2 over 9 pi. And this would be, since height is measured in meters, this is meters per second, since we are measuring the rate of change of the height. Hey, that's correct. Nice. If you want the decimal answer, it's about 0.071 meters per. Oh, it's meters per minute. I apologize on the unit there. Since it's 8 meters per minute was the unit, so whoopsie. There you go. I like the exact answer. And on the AP test, they'd take both. In which case, you should probably err on the exact answer. Use this one. Don't use the decimal version unless you want to run the risk of getting the problem wrong at the last minute by not rounding correctly. Boo. Next question is 780. I really only care about question B here. I do not care about A very much, but we're going to have to think about A at least to get to B anyway. We are talking about the wedding cake. We had a problem like this on a previous homework problem. Kiki is still trying to decide on her wedding cake. She's decided to keep the same shape and size but have 8 layers. Whew. So, if I'm going to draw this cake, I'm just going to try to map it out. What we're going to do is we're going to have 8 different layers. Each one is a cylinder. The next layer is going to look something like this. And the next layer will look something like this. And the next layer will look something like this. Kind of like this. Yeah, you see what I'm going for here? Yeah, it's going to be like a big old 8-layer cake. I'm trying to draw my best 3D drawing. The calculus idea we're getting for Chapter 8, our final chapter, which we're going to have to blow through real fast, is the idea of adding together several rings in order to approximate a 3-dimensional area, which is exactly what's going on here. Now, we're just going to map this out and hope to establish a pattern, because we're going to find the volume of this latest design. What we do know is that each layer is 2 inches tall. So the height of each one of these layers is 2, and 2, and 2, and 2, and so on. And we also know the diameters of the layers, which are 16, 14, 10, 12, 8, 6, 4, and 2. So these are all of them cylinders. And the volume of a cylinder is pi times the radius squared times the height. So we are really just going to add together a bunch of cylinders. Each cylinder has a height of 2. And so the only variable left here, the volume of each one of these cylinders, is going to be 2 pi times the radius squared. Now, we don't need to think about a Riemann sum for this. I'm going to map out the first couple and show you what's going on here. The first one has a diameter of 16 and therefore a radius of 8. So the total volume, I'm going to say volume sum, the first one is going to be 2 pi times 8 squared. The next one will be 2 pi times 7 squared. The next one is 2 pi times 6 squared, and so on. 2 pi times 5 squared, 2 pi times 4 squared, and then all the way up to the one that has a radius of, or a diameter of 2, and therefore a radius of 1. Tablet is acting funky today. Do I need to write 2 pi every time? No, you could easily factor out 2 pi in front. In fact, the correct Riemann sum for this would look something like this. It'd be 2 pi times sigma from I equals 1 to 8. And that would take care of, or I guess, or you can go 0 to 7, I suppose, would be a better way to think about that. And we would go, in order to map out from highest to lowest, we would do 8 minus I squared. So that's 2 pi times the radius squared. And if you plug in 0, you use 8. If you plug in 1, you use 7. If you plug in 2, you use 6. All the way down to plugging in 7, which uses 1. Now, we could use a calculator to approximate this, or you could use your calculator to just add up all of the areas. It wouldn't be a big deal. It takes about the same time for all of them. So I'm going to do 2 times pi times 8 squared plus 7 squared plus 6 squared plus 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared. And eventually we're going to think about this as an integral, which is actually a lot easier than it sounds. This is going to be about 1281.76, I guess 770, if we're rounding correctly. And the unit would be cubic inches, since everything is measured in inches in this problem. We're setting up for a topic, one of the last topics we got to talk about this year. We are not going to do 781 because it's dumb and we don't need it. 782, we're going to let the calculator do most of the work for us on this problem also. All we need to do is set up this problem, and trust me, it's not going to be that difficult. We did skip a problem that used this setup on the last assignment, so we're going to kind of think about this. This is our city that straddles the Newton River. The city is applying for a National Parks and Recreation Funds and needs to know the area of the land within the city limits. The area of the land is shaded in the diagram. So we're given the equation to the river banks. The north bank is this cosine-looking expression, which I assume is this waveform right here. And the natural log of 9 minus x is this kind of like exponential-looking curve right there. Now our job is to find the area of the land, which we might need to think creatively about how we're going to express this. We are just going to use some integrals, since integrals can easily measure the area under the curve. What we're going to do is we're going to think about this big square here. It's a 10 by 8 square, 10 mile by 8 mile square. And what we're going to do is we're going to do a couple clever subtractions. This green area that I'm drawing now would be the integral on the area under the curve of the cosine expression, and that would include the bank or the land underneath that natural log expression. So what we're going to do is we're going to start with 80, which is 8 times 10. That would be the area of the square. We're going to subtract the integral from 0 to 8 of that cosine expression. Cosine of pi x over 2 plus 6. And we're going to put that in parentheses and put a dx after it. Because remember, we're using tiny rectangles to approximate an area under the curve, like that. Now that will not be the final answer, because that would just be the area of that whole green space that I highlighted. We need to then add on the area under the curve of the natural log function, which, I see I'm going to need, a pen for this. We need to add on that red area there. So we're going to add it back, is what's going to happen here. So we're going to add to that the area from 0 to 8 of the natural log expression, which is the natural log of 9 minus x. We are going to let the calculator handle all of the muscle for this problem, because we mapped it out. All we got to do is now tell the machine what to do. So let's tackle that. We're going to be very careful about this. We're going to start with 80 minus the integral. We're looking at the area under the curve from 0 to 8 of the cosine of, we'll make a fraction here. It's pi x over 2. And then we'll put a closed parentheses plus 6. Whoops, plus 6, I said. dx. Again, that is just the area of the green space. We need to add back the integral from 0 to 8 of the natural log expression, the natural log of 9 minus x dx, like that. And that should, in theory, this should give us what we're looking for. Now, could we do this by hand? Could we evaluate those integrals? Sure. But why would we? This is the kind of question that would be on your calculator active section of your test. And so use the calculator, 43.775. It's probably miles, square miles, because the 8 and the 10 are measured in miles, like that. Remember your units, don't forget that. Got to have those. See, simple. I like this problem more as an exercise in how do you set up an integral that correctly expresses what you're looking for, and for that, I really like it. Okay, I need my zoom feature to come back. Okay, let me zoom. My tablet's acting all sorts of funky. Oh, there we go, okay. And 783, I like this as one last exercise. We haven't done this in a long time, but this is translating the sigma notation, which here we fortunately have written as a limit, into an integral. So really thinking about what this integral is going to be. There actually are a lot of different answers for this, but let's break down why there are a bunch of different answers and think about what we're going to write. First of all, if you think about how we usually think of an integral, the area under the curve of some function, you have your lower bound and you have your upper bound, A and B, and what we do is we chop them up into infinitely many small, tiny rectangles. The way we usually think about one of those rectangles, let's draw a generic one on here and then zoom it up. We think about the width of that rectangle as dx, and then the height of that rectangle is the function, f of x, like that. Now the dx, we used to, way back before we sent it to infinity and made it an infinitely small, tiny slice, dx is actually measured by taking b minus a and dividing it by the number of rectangles. Now I see that represented right here in front of the fraction, 6 over n. What that says to me is that b minus a has to be 6. So you can put, I think, pretty much any answer that you want here for that. But anything, as long as they're 6 apart from each other, I think you're good to go. So I'm going to go ahead and put 1 and 7 down. Now, as far as what the actual function is, I'm seeing this 1 over n plus 3 thing happening here. So what I'm thinking is, I gotta think about this for a minute here. It's gonna be something plus 3. I'm thinking 1 over x plus 3. I think is probably the best answer. For this 1 over x plus 3 or yeah, I think 1 over x plus 3 is a good answer for this question. I think that's going to be right. Or I'm going to stick with that. It might, I'm going to put a star next to this one. The more I think about it, I don't like that it's not sigma notation. I feel like I'm missing something with the 1 over n plus 1 over n, 1 over n, 2 over n. So I don't know. I got to think about this for a minute. What's the function? I'm plugging in 1, 2, and then all the way to n. So actually, yeah, I kind of like my answer. The more I think about it, oh well. I'm gonna leave it like this. I'm gonna put a star next to this problem. I'm gonna include it in the homework, but I'm not gonna require it. I'm gonna say like, hey, look at 783 for fun. Anyway, my 6th-hour class is gonna show up because it's currently 5th hour and you guys aren't here, and I miss you very much. But you guys are awesome, and I will see you in the next video. Keep it up. You guys are doing great. You're almost to the end. You're almost there. I can feel it. You're so excited, and I can't wait for you to make it to the end. You're gonna be great. So I'll see you in the next video.